Okay, in this problem, we're going to look at how you can determine what altitude and speed you want to give a satellite for it to have a stable orbit with a specific period. We're going to use the period of 12 hours. So this satellite is going to be, so if this is the Earth, here's the satellite. It's going to go around the Earth all the way in a 12-hour period. Okay? And what we want here is we want this circular motion to be maintained by the force of gravity, and we're hoping it's far enough away from the Earth that there's no wind or other resistive forces. And so this thing, if the force of gravity is equal to the net force that it requires for its circular motion, or the centrifugal force, then it should be in a stable orbit. It should just keep orbiting around and around. So the force of gravity, we have to use the universal equation here because this object is obviously significantly far away from the Earth. So G, mass of the Earth, mass of the satellite, divided by the radius of the Earth to the satellite, is equal to the formula for centripetal acceleration, so the mass of the satellite times 4 pi squared r, again that's the Earth to the satellite, divided by the period squared. Oops, I made a little mistake here. This formula for the force of gravity should be radius of the Earth to the satellite squared. Now I notice that the mass of the satellite is on both sides of the equation and it can't equal 0, so I'm going to cancel them out. And then I get a formula here where I know everything except for the radius from the Earth to the satellite. So I'm going to solve for that. I'm going to bring the period up to this side. I'm going to bring these two radiuses, radius squared, up here with this radius, and I'm actually going to end up with radius Earth to satellite cubed. Then I'm going to divide both sides by 4 pi squared. So I'm going to get the radius of the Earth to the satellite cubed is equal to GME period squared divided by 4 pi squared. Now I can cube root both of these things, and that will cancel that out, and I'm just left with the radius of the Earth to the Sun. Now, this is going to be sort of a big calculation here, but it's just plugging numbers into the calculator, so it's nothing too hard. We just got to do it. So that's G, the universal gravitational constant, mass of the Earth, times the period squared. Oops, I forgot to do that. It's 12 hours. We need that in seconds, right? Because that's our standard unit for time. So we're going to convert hours to minutes, and then we'll convert minutes to seconds. In 1 hour, we have 60 minutes. In 1 minute, we have 60 seconds. And so 12 hours in seconds is 43,200. So that's how many seconds there are in 12 hours. So put that in here, 43200 squared divided by 4 times pi squared. And then I have to cube root all that, and that will give me my radius from my Earth to the Sun, or this distance right here. So when I have a big calculation like this, my habit is to type it in twice. That sort of just acts as a check to make sure that I didn't hit a wrong button. The chance that I hit a wrong button on a calculation like this is pretty significant. But if I type it in twice, the chance that I make the same mistake twice is pretty low. So I just typed all that in. I got 2.66 times 10 to the 7 meters. And I'm going to just do the exact same thing again. This is just a check. So 6.67 times 10 to the negative 11, 5.98 exponent 24. That's the mass of the Earth, 43200 squared, divided by 4, divided by 3.14, divided by 3.14. And I will cube root all that, and I get the same thing, 2.66 times 10 to the 7. So I checked it, so I'm happy with that. Now the question actually says the altitude. I don't know if I'd be picky about this, but I think technically this section right here, that's the altitude. So we don't include the radius of the Earth in that. So if I want the altitude, I guess I should take the radius of the circular motion less the radius of the Earth. Again, just looking off a chart for this value, the radius of the Earth is 6.37 times 10 to the 6 meters. That's the average, but that's what we'll use. And I get an altitude of 2.03 times 10 to the 7 meters. Again, I don't know if this step is really necessary. I mean, that's the technical definition of altitude. As long as you were clear about what you had found, I think that that was okay, but we'll just be specific here. So that's how high up you'd have to be, 2.03 times 10 to the 7 meters, or 20,000 kilometers. How fast would you be going so that you would maintain this orbit and you would get around without falling to the Earth? Now that I have this radius, I can just start with this basic assumption that the force of gravity is causing the circular motion, and then I can, again, put in these values. And now that I know the radius, this is going to be a little bit easier to solve. Now I'm going to use this formula for circular acceleration because it gives me my speed directly, so that makes that relatively easy. And here, the mass of the satellite isn't 0, and the mass of the radius isn't 0, so I can divide those guys out, and I get that the speed is just the square root of the universal gravitational constant, mass of the Earth, divided by the radius that we're working with here. So, I mean, there's lots of ways to do the second part of the problem. This is just an easy way that I think. Times 10 to the 24 divided by that radius. Here we want to make sure we're using the whole radius of the circular motion. And I get 3,872 meters per second. So that's the speed I'd need to be going at. So I have my altitude, or if you just want the radius of the circular motion, and my speed. And if I have that speed at that radius, then the force of gravity will just be enough to maintain a stable circular orbit or a stable orbit.